So we're going to do 4 more examples, just to kind of show you a little bit more of this, how this works. So we're asked to find a polar equation for the curve that's represented by the equation x times y equals 4. So we are looking for r and theta and no x and no y. Okay, what do we know? Well, x is equal to r cos theta always. That's how we convert between polar and Cartesian coordinates. Y is equal to r sine theta always. Okay, so what does this equation become? Well, r cos theta times r sine theta equals 4. We can collect our terms a bit. Cos theta sine theta equals 4. We can make our lives a little bit easier by observing that this is the identity 1/2 sine 2 theta. Well, that gives us that r squared times 1/2 sine 2 theta is equal to 4. We can rearrange a bit and get that r squared is equal to 8 over sine 2 theta, which is the same as 8 cosecant theta. And I'm happy to leave it there. Okay? What are we doing? We're recognizing that x is r cos theta, y cos theta, y is equal to r sine theta. Then we are substituting those values in to our equation, collecting, rearranging as necessary. Next, so this is an example that we used the graph of this. We used it here. Okay, so that is our target. Let's see if we can reason our way through it using our knowledge of the Cartesian coordinate system. So we're going to start with we want to study this relationship between r and theta, okay? Study relationship between r and theta in Cartesian coordinates, because that's our most familiar place. Okay, so we start as high as 2, we go down as low as -2, and we have this action going on. Okay, now you are very welcome to think through like where in the world these intersections and these peaks and the valleys happen. I will do a little bit of it. Okay, this point is pi over 6. Okay, why is that? When you substitute theta, so this is my theta axis, this is my r axis in the Cartesian coordinates. Okay, so theta is equal to pi over 6. Plug that into my r, and I get 2 cos of pi over 2. Well, that's 0. Okay, and so that's where that value is coming from. The period of this thing, it's 2 pi over 3. Okay, and so we're going. So this is pi over 2. Here we have 5 pi over 6. Here we have pi over 3. Here we have 2 pi over 3. All right, and that's fine. I urge you to take some time and do this a little slowly, especially if you're getting overwhelmed by me plugging them in. It takes a little minute. Also, you're welcome to use your tools out there to kind of figure this out. Okay, so now we're going to talk about polar coordinates. So here they are. What are we going to do? Well, let's plug some points in that we do know. Well, when theta is equal to 0, r is equal to 2, so let's place that point here. Okay? Great. Okay. When theta is equal to pi over 6, okay, so that's, you know, maybe I should be using theta is equal to pi over 6. That's this ray. Well, we're kind of like sweeping out, and then we get this point, pi over 6, back at the origin. Okay? And so we're got this action happening here. Okay? And that maybe shouldn't be actually touching the ray, but that's okay. All right? And then what happens? Well, we sweep down. We continue sweeping our I'll use my pen, you can see it, okay? We're sweeping around looking at various angles and the values of the r that pop out, okay? All right? And so what is going on here? So maybe so that's this thing, all right? Now, what is happening next? Well, we are going to start getting negative r values, okay? And our like this point here that we're interested in, that's at pi over 3. So that's this ray, okay? But my r values are becoming negative, okay? And so instead of going up like this and getting that high point of positive 2, we're actually sweeping out over here. Okay, and we're getting those ones. All right, so I'm going to erase those. Whatever. Okay, and so we get this values, okay, and then we sweep back here, and then we head out like this, and we head out like this, and we head back around like that. And so, like, doing these things in order can be very, like, you want to think about, like, okay, so like I'm looking for values along this ray, but now I have negative values, so I'm actually over here. And I want to think about values up here, but I actually have negative values down here. And like it takes some doing, right? It absolutely takes some doing in order to get competent and comfortable doing this stuff, okay? But I do want to urge you to kind of like try thinking about some test points and how this stuff is interacting with each other. So I'm going to erase that, which is not what I want to do. I was just trying to make that get filled in. Okay, so this is my ray. This is 2 pi over 3. This ray is 4 pi over 3 down here. And pi over 3 here. This is pi over 6. Okay, and so studying our interesting points as we sweep around is where the action happens. Yeah, we can do this one. Identify the curve by finding our Cartesian equation for the curve r equals tan theta secant theta. Okay, let's figure out what this is. Well, r is equal to tan theta secant theta. Let's start by just kind of like getting rid of the tan and the secant. I'd rather work with sines and cosines. Tangent is sine over cosine. Secant is 1 over cosecant. So I have sine theta over cos squared theta. I can rearrange that a little bit, and I get our cos squared theta is equal to sine squared theta. Okay, now what? Well, let's I'm going to multiply both sides by r to see. So I get r squared cos squared theta is equal to r sine theta. Now, why in the world am I doing that? Well, this thing, that looks like y, right? I can rearrange it further and get r cos theta all squared equals r sine theta. This thing, that looks like x. This one looks like y. So what do we have? X squared equals y. In this case, definitely prefer the Cartesian coordinates. Looks a lot nicer than these polar coordinates. And that's where I'm going to leave these 3 examples. I'm going to start a fresh video for the last one, which has some calculus in it, derivatives.